the beginning of our understanding, time seemed so obvious that no one questioned it. Each second ticked away, unchanging, steady, eternal. A child grew older, a tree stretched higher toward the sky, the seasons turned, and everything followed a rhythm that appeared absolute. Time was treated as the great stage upon which the universe performed, but never as an actor itself. It was invisible, yet taken for granted. In the centuries before Einstein, this assumption was rarely challenged because in daily life it seemed perfectly true. Isaac Newton gave this vision of time its most famous mathematical form. For Newton, the universe was like a vast, ordered clock. Space was the box in which everything was placed, and time was the ticking rhythm that kept events moving forward in perfect order. He believed time flowed uniformly, the same for everyone, no matter where they were or what they were doing. The beating of the cosmic clock never faltered, never stretched, never slowed. This view was so convincing that it became woven into the way science itself operated. Equations of motion, planetary orbits, falling apples, the tides of the oceans, all could be calculated using the assumption that time was a universal background, smooth and unchanging. This was the Newtonian age, and it gave humanity tremendous predictive power. The planets could be mapped with unprecedented accuracy, cannonballs could be fired with mathematical precision, and engineers could build machines that worked reliably because their movements could be timed against this constant flow. It made time feel not only real, but dependable. The heart of this worldview was the belief that the universe obeyed strict laws written on the canvas of absolute time and absolute space. And yet, hidden beneath the surface of this certainty, questions lingered. Philosophers had already been debating the nature of time long before Newton set his ideas to paper. Gottfried Leibniz argued that time was not an independent thing, but only a way of measuring the sequence of events. Immanuel Kant believed that time was a category of human perception, a structure our minds imposed upon reality rather than something out there existing on its own. These were not mathematical arguments, but they revealed the unease with declaring time as something absolute. Even as Newton's equations triumphed in the world of mechanics, the philosophers insisted that time might not be as simple as it appeared. Still, the everyday experience of people reinforced Newton's vision. A clock on a tower struck the same for everyone who heard it. Two people standing on opposite ends of a city could agree on the time of day simply by comparing their watches. When trains began to crisscross continents, entire nations standardized their clocks so timetables could be coordinated, and this seemed only to strengthen the impression that time was something universal, flowing like a river that never changed speed. It felt natural, inevitable, unquestionable. The power of this illusion was so strong that even when experiments revealed puzzling behaviors in light and electromagnetism, scientists clung to the Newtonian picture of time. They invented hidden mechanisms like the ether, a supposed invisible medium filling space, to preserve the idea of absolute reference. It was as if the mind of humanity could not let go of the certainty that there was a single, universal now, ticking forward for everyone alike. But cracks in this vision were already forming. Astronomers measuring the motions of planets noticed small deviations that Newton's equations could not easily explain. The speed of light appeared to remain the same no matter how the observer moved, defying expectations. The stage of absolute space and absolute time was beginning to wobble, even if no one was yet ready to tear it down. To live in the Newtonian age was to live in the comfort of certainty. Time felt like a metronome, indifferent to human lives, yet universally binding them together. And this comfort made what came next all the more shattering. Because when Einstein arrived, he fractured time itself. What seemed eternal and absolute became fragile and relative. The great clock of Newton was broken, and the universe revealed a deeper, stranger truth. Time had always been treated as the quiet backdrop, the silent drumbeat marking the rhythm of existence. People trusted it instinctively, the same way they trusted that the sun would rise each morning and set each evening. A farmer rising at dawn, a sailor charting the stars, a child waiting for the school bell, all lived within this unquestioned rhythm. Even when the world seemed chaotic, time was thought to remain steady, untouched by storms or wars. It was the hidden order in a universe that often felt unpredictable. Newton's genius was to give this order mathematical flesh. He wrote of time as flowing equably, without regard to anything external. These words carried immense authority, and for generations they were repeated in classrooms, inscribed in textbooks, and applied in every corner of science. When people built pendulum clocks and synchronized them across cities, they felt they were confirming Newton's truth. Two observers, no matter how far apart, could measure intervals of time and agree completely, because it was believed that the flow of seconds was identical for everyone. Yet human beings have never been content simply to measure. They long to understand. What is time? Is it a thing in itself, like a river flowing past us? Or is it only a way we organize our perceptions? Leibniz resisted Newton's claim, suggesting that time had no reality, independent of the events that occurred within it. He compared time to a language, a system of ordering, but not an object that existed on its own. Later, Kant would argue that time was a form of intuition, a necessary framework through which the human mind perceives reality. For Kant, to imagine a world without time was impossible, not because time was part of the external world, but because it was a precondition of how humans experience that world. These philosophical arguments never shook the authority of Newton's mathematics, but they lingered like shadows. While the philosopher might say that time was only a mental construct, the engineer could point to a working steam engine timed to the rotation of gears and wheels, and declare that time was as real as iron and coal. The certainty of Newton's time was practical, useful, and it worked. For most people, that was enough. The 19th century deepened this trust. As railways spread across Europe and America, schedules became essential. Towns that once kept their own local time were forced to adopt standardized time zones, so trains could be coordinated across long distances. Telegraph wires hummed with signals used to synchronize clocks across continents. People began to live not only by the rising and setting of the sun, but by a new rhythm of mechanical time, industrial time, railway time. And this seemed only to prove Newton right. Time was universal, objective, shared by all. But hidden within the new technologies were hints of a deeper strangeness. The telegraph transmitted signals at nearly the speed of light, forcing scientists to confront the nature of that speed. Experiments by James Clerk Maxwell suggested that light did not require a medium to carry it, and that its speed remained constant regardless of how it was measured. This was profoundly unsettling. If time and space were absolute, then motion should alter the apparent speed of light. But observation said otherwise. To preserve the Newtonian vision, scientists proposed the ether, a mysterious invisible substance filling the cosmos, a medium through which light waves supposedly rippled. For decades, this idea was treated as self-evident because it allowed absolute time to survive unchallenged. If the ether existed, then motion could be measured against it and the old order would hold. But the more carefully scientists searched, the more elusive the ether became. Meanwhile, the everyday human experience never revealed these subtleties. No one walking to a market or setting a pocket watch noticed any discrepancy. A second seemed the same for all. The uniform ticking of clocks on mantles and towers reassured people that Newton's framework was sound. What could be more obvious than the fact that time advanced equally for everyone? Yet the cracks in certainty widened. Observations of Mercury's orbit revealed tiny deviations that Newton's equations could not explain. The Michelson-Morley experiment, one of the most careful measurements of the 19th century, failed to detect the ether at all. Still, the idea of absolute time was so powerful, so deeply woven into human thought, that even faced with mounting evidence, scientists hesitated to abandon it. The stage was set for a revolution. Time, which had seemed so solid, so eternal, would soon be revealed as fragile. The coming century would show that clocks did not always agree, that simultaneity was not universal, that the river of time could bend and twist. The Newtonian illusion of emptiness, where space and time were nothing more than a neutral backdrop, was about to collapse. And when Einstein appeared, with equations as simple as they were shocking, the entire stage shifted. Time itself cracked open, revealing a universe far stranger and more beautiful than anyone had dared to imagine. Time, in the Newtonian imagination, was the ultimate certainty. It was the silent ruler that never bent, never wavered. And yet, the more carefully people observed the universe, the more nature seemed to whisper that something was wrong. The cracks were hairline at first, tiny discrepancies in the motion of planets or the failure to detect the ether, but they deepened into fissures that no amount of patchwork could cover. The world clung to the illusion of universal time because it was comfortable, because it felt right, because it matched the rhythm of daily life. But illusions can hold only so long when reality insists otherwise. The closing years of the 19th century carried within them the seeds of a revolution. The Michelson-Morley experiment had not only failed to find the ether, it had raised a deeper question. If there was no universal medium filling space, then what was motion relative to? Newton had claimed that motion was measured against absolute space and time. But if light traveled the same speed no matter how one moved, then this absolute backdrop could no longer be trusted. The certainty that every observer shared the same ticking clock began to unravel. Imagine the unease of that moment. For centuries, scientists had built their calculations on the assumption that time flowed the same for everyone. But the data hinted that perhaps observers in motion measured events differently, that perhaps even the very order of events could be seen one way by one observer and another way by another. Such an idea was nearly unthinkable. And yet, like a storm gathering on the horizon, it loomed ever larger. Philosophers had long warned that time might not be what it seemed. Kant had suggested that time was woven into the fabric of perception, not into the fabric of the universe. Leibniz had argued that time was no thing at all, merely the succession of events. Now physics itself, which had once promised certainty, seemed to be catching up to these unsettling intuitions. The ground was shifting, the old confidence was faltering, and still, in ordinary life, the illusion remained intact. A farmer could still wake at dawn. A child could still count the seconds on a pocket watch. A conductor could still call out the schedule of a train, and no one would notice anything unusual. Time felt steady, dependable, eternal. The human senses reinforced Newton's view every day, even as science began to undermine it. It was into this world of contradiction that Einstein stepped. He was young, unknown, working in a patent office, and yet he carried within him a willingness to abandon the illusion, to see what others could not or would not see. He dared to ask, what if there is no universal now? What if time itself depends on how you move, on where you are, on the path you take through the universe? What if Newton's grand stage was not a stage at all, but part of the play itself, bending and twisting with the actors? The answer would be nothing less than the birth of relativity. In Einstein's vision, time was no longer absolute. It could stretch, it could shrink, it could warp. There was no single rhythm shared by all, but many rhythms, many clocks, each tied to the motion and gravity of its observer. This was not a correction, not a small adjustment to Newton's framework. It was a revolution. The old world was gone, and a new universe had been born. The Newtonian illusion of emptiness, where time and space existed as unchanging containers, had collapsed. In its place rose a vision more daring, more strange, and far more beautiful. The idea that space and time were a single fabric, alive and dynamic, shaped by motion and mass. The age of absolute time was over, and so the story of gravity and time truly begins, not with the comfort of Newton's eternal clock, but with the shattering moment when Einstein showed that time itself could fracture. From that fracture flowed every discovery that would follow, from the slowing of clocks in a gravitational field to the warping of time at the edge of a black hole. The illusion had ended. A deeper truth awaited. When Einstein first proposed that space and time were not separate, but instead parts of a single fabric, the idea was as shocking as it was elegant. For centuries, space had been imagined as an infinite emptiness in which objects floated, while time was imagined as an independent river flowing past everything. These two notions felt so natural, so distinct, that merging them seemed impossible. Yet Einstein saw that the clues were already there, scattered across the evidence of light, motion, and the stubborn constancy of nature's speed limit. The mystery began with light. No matter how observers moved, no matter how fast they chased after it or fled from it, light always arrived at the same speed. This was not what Newtonian intuition predicted. If a horse gallops and a rider throws a stone forward, the stone's speed adds to the gallop. If the rider throws the stone backward, the speed of the gallop subtracts. But with light, this simple addition and subtraction failed. Whether moving toward the beam or away from it, the speed of light remained unchanged. It was as if nature had locked it, refusing to bend to the arithmetic of common sense. Einstein realized that the only way to preserve this constancy was to sacrifice the old assumptions about space and time. If the speed of light was the same for everyone, then space and time themselves had to adjust to keep the books balanced. Intervals of length could contract, intervals of time could dilate, and simultaneity could vanish. The world that seemed so absolute to Newton became pliable. Consider two twins, one who remains on Earth and one who travels aboard a ship that nears the speed of light. To the traveler, time feels normal, his heartbeat steady, his meals spaced evenly. But when he returns, he finds his sibling older, while he himself has aged far less. This is not science fiction, not a trick of perception, but a real consequence of relativity. Motion bends time itself. This discovery shattered the notion of a universal now. In Newton's world, everyone shared the same present. Two events happening at the same instant were simultaneous for all. But in Einstein's universe, simultaneity became relative. Two flashes of lightning that strike different ends of a train may seem simultaneous to a person standing still beside the tracks, but not to the person riding inside the train. The very question of whether they happened at the same time depends on who is watching and how they are moving. The fabric of reality was woven differently than anyone had imagined. Space and time were no longer two independent threads, but strands braided into a single continuum: space-time. Each person, each planet, each star traced its own path through this fabric, and each path carried its own rhythm of time. The idea that there was a single, objective clock for the universe dissolved. And yet, in this strangeness lay a new kind of beauty. The laws of physics were not broken. They were revealed as deeper and more subtle. The speed of light stood as the great invariant, a beacon around which space and time bent themselves into harmony. What had once seemed like contradictions now became elegant consequences. The universe was not chaos. It was a new order, stranger and richer, awaiting exploration. But motion was only part of the story. If velocity could warp the flow of time, What about gravity, that ancient force that Newton had tamed with his equations? Einstein would soon show that gravity, too, was no longer a force pulling at a distance, but geometry itself. Space-time, that fabric newly revealed, was not merely a backdrop. It could bend, stretch, and curve. And in its bending, time itself would bow. The revelation that space and time were not absolute but flexible demanded a transformation in human imagination. The Newtonian world had been comforting because it matched everyday experience. A second on a watch felt the same as a second on another watch, no matter where or when it was measured. But Einstein showed that this was only an approximation. The deeper truth was that time was personal, bound to each observer's journey through space-time. To grasp this, imagine again the famous thought experiment of the twins. One remains on Earth, living an ordinary life, while the other boards a spacecraft capable of reaching speeds close to that of light. The traveling twin feels no strangeness. His heartbeat remains steady, his thoughts flow naturally, his meals and sleep follow a rhythm that seems unchanged. But upon returning home, he finds that his sibling has aged decades, while he has aged only a few years. Both are correct in their experience. The traveler's time did not slow for him. The stay-at-home twins' time did not race forward. Yet when compared, their clocks disagree. The passage of time is not universal. It depends on the path each has taken through space-time. This paradox, though startling, is no illusion. It has been confirmed by countless experiments. Particle accelerators produce unstable particles that decay quickly. When pushed to speeds near light, these particles live much longer than they would at rest. Their internal clocks have slowed relative to the laboratory's frame. Atomic clocks flown aboard airplanes and satellites tick differently than those left on the ground. Their rates shifted by motion, as Einstein predicted. The twin paradox is not only a story, it is nature's law. But perhaps even more unsettling is the loss of simultaneity. Consider a train rushing down the tracks. To a person standing on the platform, two lightning bolts strike the front and rear of the train at the same moment. The flashes rush toward the middle, reaching an observer who stands equidistant between them. He declares them simultaneous. Yet to an observer aboard the train, moving forward, the flash from the front must travel farther to reach her, while the flash from the rear meets her more quickly. In her frame, the strikes did not happen at the same time. What one observer calls simultaneous, another calls sequential. There is no universal present, no single now shared across the cosmos. The comforting notion that everyone moves through the same slice of time together is gone. Instead, each observer slices space-time differently, and their slices rarely match. This is not an illusion of perception, but a real feature of the universe. To human intuition, this feels impossible. Daily life never reveals such contradictions. People walk, talk, and breathe within speeds so tiny compared to light that relativity hides beneath the surface. Seconds appear equal because the differences are too small to notice. But when speeds climb, the truth emerges. Time is pliable. The present is relative. The universe does not grant a shared clock. Einstein's insight reshaped not only physics, but the very philosophy of existence. The river of time was no longer one stream, but many. Each traveler carries his own current, determined by motion through the cosmos. The old dream of an eternal present, ticking the same for all, was gone. In its place stood a world stranger and more majestic, where the speed of light binds reality into a new order, and time itself bends to the path one takes. Yet motion was only half the story. If velocity could distort time, what would mass do? Newton had said that mass pulled at a distance with invisible force. But in Einstein's growing vision, gravity was not a force at all. It was the warping of space-time itself, and wherever space-time bent, time would bend with it. Einstein's vision reached its most profound form when he asked humanity to abandon the idea of space and time as separate entities altogether. If lengths could contract and clocks could slow, then what people had once thought of as two independent backdrops were in truth woven into one single tapestry. That tapestry was space-time, and every object, from a falling apple to a distant star, traced its own path across it. To see this, picture space-time as a vast grid. Each line running horizontally represents space, each line running vertically represents time. In Newton's imagination, the grid is rigid, unchanging, the same for everyone. But in Einstein's vision, the grid is flexible. Move faster, and your line through the grid tilts, stretching your time compared to others. Stand still, and your line rises steadily upward. The geometry of motion itself defines how you experience time. The brilliance of this idea was that it did not destroy the laws of physics, it restored their harmony. For centuries, scientists had struggled to reconcile the stubborn constancy of light with the shifting speeds of motion. Relativity resolved the conflict at once. The speed of light was absolute, while space and time gave way. Each observer could disagree about distances and durations, but all agreed about the laws themselves. Nature's bookkeeping remained flawless because the very fabric of reality flexed to preserve it. This was not a metaphor, but a literal change in understanding. Time became the fourth dimension, inseparable from the three of space. Events were not simply located in space or in time, but in space-time. A meeting between two people was not only in a place and at a moment, but in a single point within the fabric. To alter motion was to alter time. To alter time was to alter motion. They could no longer be pulled apart. Einstein often explained that people could not speak of space without time, or of time without space. The two were like threads in a single cloth. Tug on one and the other shifted with it. This is why no universal now could survive. Each observer's slice through space-time was different, each shaped by the trajectory of motion. And though these slices did not align, the laws remained consistent. What one observer saw as stretched, another saw as compressed. But the speed of light and the equations of physics stood unbroken. Experiments would confirm this again and again. Moons, short-lived particles created in Earth's atmosphere, survive far longer when racing toward the ground than when at rest, because their clocks are slowed by their tremendous speed. Atomic clocks flown aboard jets tick more slowly than those left on Earth. Satellites in orbit must account for the dilation of time, or their navigation systems would drift and fail. These are not tiny quirks, not curiosities, but fundamental truths. Humanity has built entire technologies upon them, from particle physics to global positioning. What began as a challenge to the Newtonian illusion became the foundation of a new reality. Space-time was not an empty stage, but the central actor. It was alive, flexible, and personal. Each path through it carried its own rhythm of time. To walk, to fly, to orbit a planet, to sail near the speed of light, each was to move not only through space, but through time at a different pace. And yet, Einstein was not finished. The realization that space and time formed a fabric raised a deeper question. What happens when mass enters the picture? If velocity alone can alter time, what of the immense gravities of stars, planets, and black holes? Could the very presence of matter reshape the fabric itself? Einstein's next leap would answer yes. Gravity was no longer a mysterious force acting at a distance. It was the curvature of space-time. And if space-time could curve, then time itself could bend, slow, and warp in ways even stranger than motion had revealed. The stage was ready for the next act, where gravity became not only the master of motion, but the master of time. The insight that space and time were one fabric was already revolutionary, but Einstein was not satisfied. He knew that velocity alone could not be the end of the story. The world was filled with planets, stars, and galaxies, whose immense gravities held them together. Newton had described gravity as a force, a mysterious pull that reached across emptiness. His equations worked well enough to send cannonballs arcing through the sky and to trace the orbits of planets. Yet Newton himself admitted that he did not know how this force acted at a distance, only that it did. Einstein set out to dig deeper, to strip away the mystery, to see if gravity itself could be reimagined through the new lens of space-time. The key was a moment of simple yet profound realization. If motion could change the flow of time, perhaps acceleration and gravity were connected as well. Einstein began with a thought experiment. Imagine a man inside a sealed elevator floating in the emptiness of deep space, far from any planet or star. The elevator is pulled upward with steady acceleration. The man inside feels pressed to the floor, just as if he were standing on Earth. If he drops a ball, it falls to the floor of the elevator with a steady rhythm. From his perspective, acceleration and gravity are indistinguishable. This was Einstein's equivalence principle, and it became the seed of his greatest leap. If acceleration could mimic gravity, then perhaps gravity itself was not a force at all, but something geometric. Einstein's imagination turned the idea into a new picture of the universe. Massive objects, like stars and planets, did not pull through invisible strings. Instead, they bent the fabric of space-time around them. To move in a curved space-time was to feel what Newton had called a force. An apple did not fall because Earth pulled it, but because space-time around Earth was curved, and the apple's straightest path led it downward. In this picture, time could no longer be trusted as steady. Where mass bent space-time, the very rhythm of clocks bent too. A clock near a massive planet would tick more slowly than a clock far away. The flow of time itself was reshaped by gravity's geometry. The same fabric that determined the paths of planets determined the beating of every second. To describe this mathematically, Einstein turned to the language of geometry. He used the tools of tensors and curved surfaces. Where mass told space-time how to curve, and curved space-time told mass how to move. The equations were daunting, yet their meaning was simple. Gravity was geometry, and time was part of that geometry. The old force acting across emptiness had vanished, replaced by a vision in which matter and time were woven into one cosmic dance. The implications were staggering. If mass could bend time, then time itself was not universal. Two observers at different heights above Earth would not agree on the flow of seconds. The stronger the gravity, the slower the clock. The concept of a single cosmic time vanished forever. Every pocket of the universe carried its own rhythm, dictated by the bending of space-time. This was more than a scientific theory. It was a reshaping of reality. The steady metronome of Newton's universe had been broken once again, and in its place rose a world where even time bowed to the presence of mass. It was a world stranger, more beautiful, and far more challenging than anyone had expected. And yet, what did this mean in practice? Could such a bold idea ever be tested? Could humanity truly measure the slowing of time under gravity? Or was it destined to remain a vision, too subtle to confirm? The answer would come not from imagination alone, but from experiments, some of the most delicate ever attempted, which would reveal that gravity truly does warp the flow of time. Einstein's vision was daring, but it was also precise. The equivalence principle, that simple thought experiment of the man in the elevator, became the guiding star for a new theory of gravity. If acceleration and gravity could not be distinguished, then every effect caused by acceleration must also appear under gravity. Light in an accelerating elevator would bend toward the floor. Therefore, light passing near a massive star must also bend. Time in an accelerating frame would slow compared to time in free fall. Therefore, time near a massive body must run slower than time far away. With these insights, Einstein set to work, and after years of relentless effort, he carved out the general theory of relativity. The mathematics was formidable. Where Newton had written simple equations of force, Einstein used geometry of curved surfaces, describing how space-time itself warped in response to matter. It was a radical departure. Mass was no longer an actor moving across a stage. It was part of the stage itself, reshaping the very fabric of reality. The sun did not pull Earth with invisible threads. It curved space-time, and Earth simply followed the straightest possible path in that curved geometry. What was most startling was how this new geometry captured time. In Newton's picture, time was an external ruler that ticked the same for all. In Einstein's world, time was a coordinate woven into space-time, and space-time could bend. The result was unavoidable. Time itself must bend. Clocks nearer to a source of gravity would tick more slowly, while those farther away would tick more quickly. The flow of seconds, once thought universal, was revealed as relative to position in the gravitational field. Einstein illustrated this with his elevator once more. Imagine that a beam of light is emitted from the ceiling of the accelerating elevator and travels toward the floor. To the man inside, the elevator rises while the light descends, so the beam lands slightly behind the point directly below its origin. To him, it appears as though the light has curved. But according to the equivalence principle, this same bending must occur for light in a gravitational field. This was not only a prediction of bent light, it was also a prediction of gravitational redshift, the stretching of light waves as they climb out of gravity's grasp. And because frequency and time are bound together, the stretching of light meant the slowing of clocks. It was an astonishing idea, but Einstein trusted it because the geometry demanded it. To him, it was as inevitable as a ball rolling downhill. Time dilation under gravity was not a possibility, it was a certainty. What remained was to see if nature agreed. The first tests were bold. Astronomers watched starlight passing near the sun during eclipses, searching for the predicted bending. When the light shifted exactly as Einstein had calculated, the world was stunned. Newspapers declared that Newton had been overthrown, that space and time themselves had been transformed. Yet this was only part of the story. The bending of starlight confirmed curved space. The slowing of clocks would confirm curved time. To measure this effect directly would require experiments of extraordinary delicacy, for gravity's warping of time on Earth's surface is subtle. But the principle was already clear. A clock at the top of a tower must tick slightly faster than a clock at the bottom, simply because it sits farther from Earth's mass. A clock on a mountain peak must run more quickly than one by the sea. The differences are small, measured in fractions of a second over years, yet they are real, written into the structure of space-time itself. The beauty of Einstein's insight was that it did not merely describe motion, it explained why. Objects move not because they are pulled, but because they follow the geometry of space-time. And since time is part of that geometry, every orbit, every fall, every trajectory is also a story of time itself being bent and reshaped. Einstein had taken humanity from the certainty of Newton's ticking clock to a universe where clocks disagree, where time flows differently depending on gravity's pull. This was not just philosophy, not just speculation. It was prediction, waiting for proof. And soon, ingenious experiments would show beyond doubt that gravity does not merely govern motion, it governs time. Einstein's equations had redrawn the universe, but even the most beautiful mathematics demands the test of experiment. The bending of starlight during the eclipse of 1919 had thrilled the world, but that was only the first glimpse. If gravity truly warped space-time, then clocks themselves must be affected. This was a subtler test, more difficult to measure than the shifting of stars in the sky, but it was also the most intimate. It meant that the very rhythm of existence was not steady, but bent by mass. The idea seemed almost too strange. Imagine two identical clocks, one resting at the base of a tall tower and the other placed at its summit. According to Einstein, the clock above, farther from Earth's pull, should run faster than the one below. The difference would be tiny, imperceptible to the human eye, but measurable with enough precision. To Newton, such a claim would have sounded absurd. Time was absolute, a steady river. But to Einstein, it was geometry, and geometry left no choice. For decades, scientists struggled to detect the effect. Technology had not yet caught up to Einstein's bold vision. But as atomic clocks were developed in the 20th century, the test became possible. In 1960, Robert Pound and Glenn Rebka devised a brilliant experiment in the Jefferson Laboratory Tower at Harvard. They used gamma rays, whose frequency is tied directly to time itself. By sending these rays from the top of the tower to the bottom and back, they measured the tiny shift in frequency predicted by Einstein's theory. The result was clear. The gamma rays lost energy as they climbed, their frequency stretched. Time at the bottom of the tower ran more slowly than at the top. Einstein had been right. The confirmation was stunning. For the first time, scientists had proof that gravity truly warped time. This was not a trick of motion, not an illusion of perspective, but a real bending of the universe's clock. The river of time did not flow evenly. It slowed in valleys of gravity and sped in higher ground. Humanity had discovered that seconds themselves were not equal across the Earth. The implications were vast. Every mountain peak, every ocean shore, every orbiting satellite carried its own rhythm of time. Two people standing at different altitudes were living at slightly different speeds. The differences were small but undeniable, and in the machinery of precision, small differences matter. The old Newtonian dream of a universal clock had been shattered. The cosmos was a patchwork of times, stitched together by the curves of space-time. For Einstein, this was a vindication of a principle born in the quiet thought of an elevator. What had begun as a mental exercise became a physical law of the universe. The equivalence of acceleration and gravity, the bending of light, the slowing of clocks, all converged into one reality. Gravity was geometry, and time itself was woven into the curve. But the story did not end in the laboratory. As instruments grew more refined, as rockets and satellites climbed into orbit, the bending of time would move from the realm of experiment to the realm of daily necessity. Navigation, communication, and science itself would depend upon the knowledge that time is not steady, that gravity reshapes it at every turn. The Newtonian illusion of an eternal clock had been broken. The Einsteinian vision of curved space-time had taken its place. And with this realization, humanity was poised to step into a new era, one where the very beating of seconds was subject to the weight of worlds. The moment had arrived to face Einstein's prediction not as philosophy or as abstract mathematics, but as reality that could be touched and measured. If gravity was the curvature of space-time, then clocks themselves must reveal it. The ticking of a second was no longer sacred, no longer identical in all places, but tied to the gravitational landscape in which it was measured. This was a profound shift. Time was no longer a background, it had become a player, warping under the presence of mass. Einstein often returned to his favorite thought experiment, the sealed elevator. Inside, a man stands unaware of whether the elevator is being pulled upward by a rocket or held by the gravity of Earth. In both cases, he feels his weight. He drops a ball and watches it fall to the floor. He shines a beam of light and sees it curve toward the ground. There is no way to distinguish acceleration from gravity. This is the equivalence principle, and it demands that time itself must be altered by gravity just as it is by acceleration. From this idea, Einstein predicted gravitational time dilation. A clock deep in a gravitational field must tick more slowly than a clock far away. A watch strapped to the wrist of a climber on a mountain would run ever so slightly faster than a watch left behind in the valley. The difference is minuscule, invisible to human senses, but real. The flow of time depends not only on how fast you move, but also on how strongly you are bound by gravity. This was a shocking claim in its day. Imagine two identical twins once again, but instead of sending one into space, place one at sea level and the other atop a high plateau. The twin at the plateau ages imperceptibly faster because time flows more quickly at altitude than in the depths of Earth's gravitational well. The effect is tiny but measurable, and when clocks of great precision became available, the prediction could be tested directly. The first attempts required extraordinary creativity. In 1960, Robert Pound and Glenn Rebka used a tower at Harvard University to measure the gravitational redshift of gamma rays. These high-energy photons, linked directly to the ticking of atomic transitions, shifted their frequency as they climbed upward against Earth's gravity. The experiment revealed what Einstein had foretold. The photons lost energy, stretching their wavelength, which meant that time at the bottom of the tower was running more slowly than time at the top. This was the beginning of a revolution. For centuries, scientists had assumed that seconds were identical everywhere, that time could be trusted as a universal ruler. Now, experiments showed that this was not true. Every location in the universe carried its own pace, shaped by the mass nearby. A clock in orbit above Earth ticked faster than one on the surface. A clock on the surface ticked faster than one deep in a mine. The rhythm of time was not fixed, but elastic. The consequences of this realization were immense. If time could be warped by gravity, then everything that depended on precise timing must account for it. Navigation systems, communication signals, even the fundamental records of science itself would have to be corrected. The universe was not a place of simple absolutes. It was a place where the beating of a second bent under the weight of the stars. But beyond the practical lay something even more breathtaking. Time was no longer a silent backdrop, indifferent to matter. It was part of the living fabric of reality. When you stood upon Earth, you were not only held by its gravity, you were immersed in its time. Every heartbeat, every thought, every breath unfolded within a rhythm slowed by the planet's mass. Time was not universal. It was local, personal, relative to the great curves of space-time. The laboratory experiments had spoken. Time itself bowed to gravity. What Einstein had imagined in the solitude of thought, nature had confirmed in the precision of measurement. And yet, these first glimpses were only the beginning. As clocks grew more accurate, and as humanity began to lift its instruments beyond Earth, the full scope of gravitational time dilation would come into view. The cosmos itself became a clock, and every star, every planet, every black hole carried its own tempo. The confirmation that gravity could slow the ticking of clocks was more than a clever experiment. It was a doorway into a universe that challenged every instinct of human perception. For most of history, the flow of time had been treated as so self-evident that no one bothered to question it. But Einstein's insight revealed that time was fragile, elastic, and tied inseparably to the mass of the world around us. Each measurement made with greater accuracy brought this strangeness out of abstraction and into the realm of daily truth. Consider again the sealed elevator, Einstein's favorite device for thought. A beam of light is sent from the ceiling to the floor, while the elevator accelerates upward in the emptiness of space. To the man inside, the light curves downward because the floor rushes up to meet it. Now replace acceleration with gravity. If the elevator rests on Earth, the same curvature of the beam must be observed. Light, which to Newton should have traveled in perfect straightness, bends in the presence of mass. And because the frequency of light is tied directly to time, any shift in that frequency means that time itself must have changed pace. The Pound and Rebka experiment gave the first proof, but technology would carry the idea further. As atomic clocks became ever more refined, scientists began carrying them onto airplanes, rockets, and satellites. These clocks were so precise that a difference of a billionth of a second could be measured. When flown high above the ground, they ticked slightly faster than their twins left behind. When taken into orbit, the difference became undeniable. Every ascent away from Earth's surface meant a gain in the tempo of time. The higher you climbed, the quicker your seconds passed. It is tempting to imagine that this is only a technical curiosity, something relevant only to physicists. But the truth is far more sweeping. The very technologies upon which modern life depends rest upon this discovery. Global positioning satellites orbit Earth at high altitude. Each carries an atomic clock that ticks faster than clocks on the ground because they are deeper into the freedom of weaker gravity. If engineers ignored this effect, the positions calculated by the satellites would drift by kilometers each day. The directions on a map, the synchronization of communications, the guidance of aircraft and ships, all would collapse into chaos. Only by accepting that gravity warps time do these systems work. The realization reshapes the imagination of everyday existence. A person living at sea level and another living in a high mountain village are not aging at precisely the same pace. The difference is infinitesimal, yet real. Billions of years of life on Earth have unfolded under a rhythm dictated by the planet's gravity. The familiar heartbeat of time that people trust has always been slightly slower than it would be in the emptiness of space. To live on Earth is to live in curved time. This knowledge carries both humility and wonder. Humility because the senses are blind to it. No one standing on a beach feels the drag of slowed seconds. No climber scaling a mountain feels his life accelerating. Yet the universe cares nothing for perception. It moves by its own rules, and human intuition must yield. And wonder, because the rules are so elegantly woven. Mass shapes space-time shapes time, and time governs the unfolding of every life. The same equations that describe the orbit of the moon describe the slow ticking of a clock in a valley. The same geometry that bends starlight bends the rhythm of seconds. The experiments that proved this were triumphs of human ingenuity, but they were also invitations. They whispered that time, far from being absolute, is a landscape. Valleys of gravity slow it, peaks allow it to run more freely. Earth is only one example. Across the cosmos, every star, every planet, every black hole sculpts time in its own way. The universe is not filled with a single clock, but with billions, each ticking at its own pace, each woven into the curvature of space-time. Einstein's insight had escaped the confines of thought experiments. The elevator had become real towers, real beams of light, real clocks carried on real journeys. The theory had become fact. The universe had revealed itself, and its message was unmistakable. Gravity does not merely hold you down. It slows your seconds, stretches your minutes, bends the very river of time. The story of clocks in a gravitational field did not end with the first confirmations. Each new generation of instruments pushed the boundaries further, peeling away the illusion of universal time with ever sharper precision. What had begun as a subtle difference measured in towers became a daily fact in the age of satellites, aircraft, and spacecraft. Time was no longer an invisible river, flowing identically for all, but a fabric stretched and squeezed by the weight of worlds. The Pound and Rebka experiment in 1960 had been a triumph, but it was only the opening movement. Soon, scientists carried atomic clocks aboard airplanes to see if Einstein's predictions would hold when machines climbed into the sky. They did. The clocks flown above the surface ticked faster than those left behind, while the motion of the airplanes themselves introduced a competing effect, slowing the clocks because of special relativity. Both influences, motion and gravity, were at play together, and the measured results agreed precisely with theory. It was the first time in history that time itself had been flown across the world and found to disagree with its twin. Decades later, rockets would lift atomic clocks into orbit, where the differences became impossible to ignore. Satellites circling Earth were both moving quickly and residing in weaker gravity. Motion slowed their clocks, while altitude sped them up. The two effects did not cancel, but combined to produce a net gain. Engineers working on the Global Positioning System had no choice but to program corrections for relativity into their satellites. Without this adjustment, navigation would fail within hours, guiding travelers far from their destinations, causing planes to veer, ships to drift, and communication networks to fracture. Relativity was no longer an academic curiosity. It had become the hidden framework of modern civilization. The precision of measurement has only sharpened with time. The most advanced atomic clocks today are so sensitive that they can detect gravitational differences across the span of a single room. Place one clock a few centimeters higher than another, and the difference in ticking will emerge. Humanity has reached the point where even the slight curvature of space-time across a human body can, in principle, be measured. Such experiments reveal not only the truth of Einstein's vision, but also the extraordinary subtlety of nature. Time does not care about the scale of perception. Whether across a mountain, a tower, or the height of a chair, gravity leaves its mark. The legacy of these discoveries is not merely technological, though that alone is profound. It is philosophical. For centuries, people believed they shared a universal present, that the rhythm of seconds was equal for all. Einstein showed that each clock carries its own truth, each tied to the fabric of space-time in which it rests. The very notion of a single time has been broken beyond repair. Humanity does not live in one flow, but in countless flows, stitched together by the curves of the cosmos. To live with this knowledge is to see the world anew. A clock on a mountaintop, a satellite in orbit, a probe flying past Jupiter, each experiences time differently. The universe is filled with rhythms, layered upon one another like the beats of countless drums. The differences are often small, but they are real, and they remind us that even something as fundamental as time is not absolute. It bends to the presence of mass. It bows to the geometry of space-time. These experiments prepared the way for even stranger truths. If Earth's modest gravity can slow the ticking of clocks, what of the immense gravities of neutron stars or black holes? If a tower on Earth can reveal dilation, what would happen near the abyss where space-time is stretched nearly to breaking? The answer would be revelations beyond imagination. The laboratory towers of Harvard were the first steps in a journey that would lead to the edge of cosmic extremes. Gravity was no longer merely the force that pulled apples to the ground or held planets in orbit. It was the sculptor of time itself. With every experiment, humanity inched closer to understanding that in the deepest regions of the cosmos, time could be twisted into forms stranger than any dream. The warping of time by motion and gravity might sound like something confined to laboratories, observatories, or the far reaches of the cosmos, yet it is not distant at all. The bending of time is woven into the fabric of daily life, silently guiding the tools and technologies upon which modern civilization depends. Though imperceptible to human senses, the differences in ticking clocks are so real and so precise that entire systems would collapse without constant correction. Relativity is not only true, it is practical. Consider the satellites of the Global Positioning System. Dozens of them orbit Earth, circling high above the surface at speeds of several kilometers per second. Each carries atomic clocks, machines so exact that they can keep time to within billionths of a second. Without relativity, one might assume these clocks would remain synchronized with those on Earth. But they do not. The satellites are subject to two competing effects. Their rapid motion slows their clocks, an effect of special relativity. Yet their altitude places them in weaker gravity, which speeds their clocks, an effect of general relativity. When both influences are combined, the net result is that the satellite's clocks tick faster than clocks on Earth by nearly 40 microseconds each day. That may seem small, but for navigation signals traveling at the speed of light, it translates into errors of kilometers. Without correcting for relativity, a map would be useless within hours. It is only because engineers account for warped time that your phone can guide you to a street corner or an airplane can cross the ocean with precision. This dependence is not limited to satellites. In the 1970s, atomic clocks were flown aboard commercial airplanes circling the globe. Upon return, they disagreed with identical clocks that had remained stationary. The differences matched Einstein's predictions. The faster-moving clocks aboard the aircraft ticked more slowly because of their velocity, while their slightly higher altitude made them tick more quickly because of weaker gravity. Both effects were measurable, and both confirmed relativity. It was as if the twin paradox, once confined to thought experiments, had played out across the skies of Earth. Even without rockets or aircraft, the effect is present. A clock placed at the top of a skyscraper ticks ever so slightly faster than one in the basement. A clock carried up a mountain runs ahead of one left by the sea. The difference is microscopic over the span of a human life, but it is measurable, and it is real. Time itself flows differently, depending on where you stand. To live with this knowledge is to recognize that the everyday world is steeped in relativity. When you look at a digital map, check the time on your phone, or rely on satellite signals to guide a ship through fog, you are depending on the corrections of Einstein's equations. Relativity is not a distant abstraction. It is the hidden framework of modern life. But there is another side to this revelation, one less practical and more philosophical. The realization that time flows differently at altitude than at sea level means that no two human beings are experiencing the exact same rhythm of existence. Every person, every mountain, every airplane, every satellite carries its own clock, beating to its own tempo. The differences may be small, but they remind us that time is not universal. It is a landscape, sculpted by motion and mass, different for each observer. The Earth itself is a patchwork of times, layered and shifting with gravity and motion. And from this patchwork, human beings have learned to build, to navigate, to explore. What once seemed like a strange prediction has become a daily necessity. Einstein's vision is not confined to blackboards and laboratories. It is carried in every signal that crosses the skies, in every journey across oceans, in every clock that beats on the surface of the Earth. And yet, if time can be warped by the modest gravity of our planet and the modest speeds of satellites, what happens when the scales are far greater? What happens when we move from the everyday world to the realm of the extreme, where stars collapse and black holes bend space-time into near oblivion? The ordinary corrections of relativity will seem trivial compared to the abyss that waits beyond. The realization that time warps even in the world around us is both unsettling and awe-inspiring. For centuries, people trusted clocks as arbiters of certainty. A second was a second, a minute a minute. and no one questioned whether the tick of a watch on the wrist was the same as the chime of a bell across the town square. Yet Einstein revealed that these instruments, however precise, are not keepers of a universal truth. They are local devices, their rhythm tied to their motion and their place in gravity's field. The experiments that proved this are among the most elegant ever devised, for they brought the paradox of relativity down from the stars and into the familiar world of airplanes and mountains. In the 1970s, Joseph Haffel and Richard Keating carried atomic clocks aboard commercial aircraft. The clocks were flown once around the world eastward and once around the world westward, then compared to their twins left behind at the United States Naval Observatory. The results were astonishing, though Einstein would not have been surprised. The eastward journey, with the plane moving in the same direction as Earth's rotation, caused the onboard clocks to lose time relative to those on the ground. The westward journey, moving against the rotation, caused the onboard clocks to gain time. Both effects matched the predictions of relativity. The experiment had taken the twin paradox, once an abstract tale of siblings divided by space travel, and staged it in the skies above Earth. These results were not subtle curiosities. The differences were measured in tens of nanoseconds, a blink to human perception, but a gulf to the instruments of science. More importantly, they confirmed once again that time is not absolute. Every journey, every velocity, every altitude shifts the pace of seconds. Human intuition insists that the world moves to one steady rhythm, but the evidence says otherwise. Clocks on Earth reveal this truth as well. Scientists have taken atomic clocks to mountaintops and compared them to clocks left at lower altitudes. The elevated clocks tick more quickly, not because they are faulty, but because they are freer of Earth's gravitational pull. Even differences as small as a few meters can now be detected by the most advanced instruments. It means that two people sitting in the same room, one standing and one seated, are aging at imperceptibly different rates. Gravity sculpts time with a delicacy that permeates even the smallest scales of daily life. These revelations have moved beyond science into necessity. Global positioning satellites, orbiting high above Earth, experience both time dilation from their speed and time acceleration from their altitude. Without constant correction, their signals would drift. Navigation would fail. Communications would desynchronize, and modern life would stumble into chaos. Engineers are forced to account for relativity every moment, not because they want to prove Einstein right, but because ignoring him makes their systems useless. Relativity is woven into every drive guided by a map, every aircraft crossing oceans, every cargo ship navigating ports. The warping of time is not confined to laboratories or thought experiments. It is here, in the pulse of technologies that connect continents. It is in the faint but real differences between valleys and peaks. It is in the nanoseconds gained or lost as aircraft trace their paths across the globe. Though human beings cannot sense these distortions, their machines must live by them. And in learning to correct for warped time, humanity has also learned to see more clearly. The world is not what it seemed to Newton. Time is not steady, not shared, not absolute. It bends with motion, and it bends with mass. This realization forces a humbling reflection. People go about their days unaware that their seconds are not the same as the seconds of those around them. Yet the universe keeps perfect account. Each clock, each orbit, each altitude ticking at its proper rhythm. The illusion of one universal time has vanished. In its place stands a richer, stranger truth, one in which every life, every journey, every place carries its own tempo. And if Earth itself already reveals such differences, then what awaits near the strongest gravities of the cosmos? What of neutron stars, so dense that mountains rise only centimeters before collapsing under their own weight? What of black holes, where even light cannot escape? The everyday warping of time is only a hint, a whisper of the extremes that await in the depths of space. The everyday warping of time is so subtle that it hides beneath the surface of ordinary perception, and yet it is so fundamental that entire civilizations now depend upon it. Without realizing it, humanity has entered an age in which Einstein's equations keep the world synchronized. The warping of time is not only something for physicists to measure in towers or laboratories, it is something that lives in the pocket of every traveler carrying a phone, in the cockpit of every aircraft crossing continents, and in the command center of every ship guided through narrow seas. Relativity is everywhere, whispering beneath the tick of every clock. The satellites that orbit Earth are perhaps the most striking example. Each one races through space at thousands of kilometers per hour, circling above the surface where gravity's grip is weaker. Their clocks, freed from the full weight of Earth's pull, tick faster than those on the ground. At the same time, their speed slows them down, a contradiction that seems impossible until relativity resolves it. The two effects are measured, calculated, and corrected so that signals remain accurate. Without these corrections, navigation would drift so badly that within a single day, maps would be useless, planes would veer from their routes, and communications would fail. The difference of a few microseconds each day, invisible to the senses, becomes a matter of kilometers when multiplied by the speed of light. That is the strange power of warped time. Even when subtle, it cannot be ignored, but the influence reaches further still. Atomic clocks have become so refined that they can measure differences across a single floor of a building. Place one on the ground and another upstairs, and the higher clock will tick ahead. The effect is minuscule but undeniable. It means that in a skyscraper, the residents of the top floor live ever so slightly faster than those at the bottom. In a valley and on a mountain peak, the same difference appears. Human beings do not feel this divergence, but nature keeps its account. Time itself bends gently, invisibly, across every contour of the earth. These discoveries alter the way humanity thinks of existence itself. For centuries, the world trusted that everyone lived within the same present. Now it is clear that there is no single present, no universal flow binding all clocks together. Each clock follows its own path through space-time, and each path carries its own tempo. The Earth is not united by one rhythm, but by countless rhythms, layered and interwoven, all held together by the curves of gravity and the motion of matter. This realization is both humbling and exhilarating. Humbling because it reveals that human intuition is blind to the deepest truths. No one feels the seconds slow at sea level or quicken on a mountain. No one senses the correction required to guide a ship across the ocean or a plane through the sky. The human mind insists that time is steady, but the universe obeys geometry, not instinct, and exhilarating because it means that the same laws that govern the bending of starlight also govern the tick of a watch in your pocket. The everyday and the cosmic are bound by one fabric, yet the everyday is only a beginning. If Earth's modest gravity and human speeds already warp time, what happens in the extremes? What happens when the mass is so dense that even light struggles to escape? Or when motion nears the ultimate limit of the speed of light itself? The answer is a universe where time does not merely slow but nearly stops, where moments stretch into eternity, where the flow of seconds becomes unrecognizable. The gentle warps of everyday life are only shadows of what waits beyond. Einstein had opened a door, and through it, humanity could see not only the subtle bending of time on Earth, but also the unimaginable warping near the cosmic abyss. the laboratory and the satellite had revealed the principle. The stars and the black holes would reveal its ultimate expression. Time, once thought absolute, was about to become the strangest and most fragile dimension of all. If Earth's gentle gravity can already slow the beating of a clock, then what happens in the most extreme environments of the universe, where gravity is no longer a subtle tug, but an overwhelming force? What happens near the monsters of space-time, the black holes, where the curvature of reality is driven nearly to breaking? Here, time reveals its strangest face. Seconds stretch into eternities, moments fracture, and the very distinction between space and time begins to blur. Black holes are born from collapse. A massive star, burning its fuel for millions of years, eventually exhausts its core. Gravity, unchecked by pressure, drives the star inward. Layer upon layer falls until nothing can halt the collapse. If the mass is great enough, no stable state remains. The star contracts beyond the limits of neutron matter, beyond any known resistance, until its density becomes so extreme that space-time itself caves in. What remains is not an object in the traditional sense, but a region, a hole carved into space-time, with a boundary known as the event horizon. The event horizon is the point of no return. To cross it is to vanish from the visible universe, for even light cannot escape its grip. But the horizon is more than a boundary of space. It is a boundary of time itself. From the perspective of an observer far away, any object that falls toward the horizon appears to slow as it approaches. Its motion grows sluggish, its signals redshift, its image freezes. To the distant eye, the object never quite crosses, never quite disappears. It hangs forever at the edge, time stretched into infinity. For the falling object, however, the story is different. The traveler plunges toward the horizon and feels no sudden barrier, no wall of fire. To her, time flows normally. She crosses the horizon in finite moments, her heartbeat steady, her thoughts unbroken. But the outside world watches her stretch and fade, her seconds elongated until they no longer pass at all. This paradox is the essence of gravitational time dilation at its extreme. Time near the abyss is not only slowed, it is fractured into two realities, one for the falling traveler, another for the distant witness. The bending of light near the horizon amplifies the effect. Photons struggling upward from the edge lose energy, their wavelengths stretched until they vanish into darkness. To watch an object fall toward a black hole is to see its light dim and redden, fading into nothing even as it continues its journey unseen. It is as if the black hole swallows not only matter, but also time itself, locking events beyond a veil that no outside observer can pierce. What Einstein's equations revealed is that gravity does not merely pull, it reshapes the very fabric of existence. Near a black hole, the curvature of space-time is so intense that time itself nearly halts. The concept of simultaneity, already fragile in relativity, shatters completely. Two observers can no longer agree on what it means for something to happen. The universe becomes a place of layered truths, each valid within its frame, yet irreconcilable when compared. This is not imagination, not speculation. Astronomers have observed stars whipping around the black hole at the center of our galaxy, their light stretched by the immense curvature of time and space. The dance of these stars, circling an invisible mass millions of times heavier than the sun, confirms that Einstein's vision holds even at the edge of the abyss. The predictions of relativity are written into the orbits of the cosmos. Yet black holes are more than tests of theory. They are windows into the ultimate question of time itself. What does it mean when time can slow to a crawl, when an object can appear frozen forever, when space and time trade roles beyond the horizon? What does it mean when gravity becomes not only the master of motion, but the master of existence? These questions lead to the edge of human knowledge, to the place where relativity collides with quantum theory, and where the mystery of time deepens into something even stranger. The abyss of a black hole is not merely a place of crushing gravity, it is a place where the flow of time itself becomes distorted beyond recognition. To stand far away and watch another object fall toward the horizon is to witness time unravel. Each step of its descent grows slower, each signal it sends weaker and more stretched. A final wave of light, emitted just above the horizon, would climb outward so drained of energy that it would fade into invisibility. From the vantage of the distant observer, the faller never crosses. He lingers in frozen stillness, suspended at the edge forever. Time, for him, has ground to a halt, and yet for the one who falls, the experience is utterly different. To the traveler plunging toward the horizon, there is no freezing, no endless stretching of seconds. His heart beats normally, his thoughts remain coherent, his sense of time unchanged. He approaches the horizon and crosses it within a finite span of his own moments. He does not feel the universe slow down. Instead, he feels the outside universe rush forward. Signals from distant stars appear to accelerate, their rhythms compressed into shorter and shorter bursts as the traveler descends. For him, the rest of the cosmos is speeding ahead, racing into the future as he slips behind the veil. This duality is not a trick of perception, but a real fracture in the way time works under extreme gravity. Relativity allows both experiences to be valid, though they contradict one another. The falling traveler experiences a crossing. The outside world witnesses a freezing. Both descriptions are true within their frames, and yet they cannot be reconciled into a single universal story. Black holes expose the ultimate consequence of relativity. There is no absolute timeline binding all observers together. Time is personal, and at the horizon it becomes unbridgeably divided. The geometry of space-time explains this strangeness. Outside the horizon, space is the dimension through which you can move freely, while time is the dimension that pushes you forward inexorably. But inside the horizon, the roles reverse. Time and space trade identities. The inward direction toward the singularity becomes as unavoidable as the ticking of a clock. To cross the horizon is to surrender to a fate written into geometry itself. You cannot choose to avoid the center any more than you can choose to stop the passing of seconds. This reversal is what makes black holes so final. Outside you may hover, orbit, or escape. Inside you have no choice. The singularity lies ahead in your future, as certain as the next moment of your life. You are drawn inward not by a force in the Newtonian sense, but by the structure of space-time itself. To speak of resisting is meaningless. You are not falling into the singularity. You are living toward it, as naturally as you live toward tomorrow. Such a vision is eerie because it defies every instinct. Human beings are accustomed to thinking of time as uniform, space as open, and gravity as a pull that can be resisted. But in the heart of Einstein's universe, these intuitions fail. Time slows near gravity, halts at the horizon, and flips its identity beyond. The abyss is not just a place where matter collapses. It is a place where reality itself bends into unfamiliar shapes. Observations confirm the edges of this truth. The black hole at the center of our galaxy, 4 million times more massive than the Sun, bends the light of nearby stars. Their orbits, some lasting only a handful of years, are warped by the immense curvature of space-time. The faint signals of matter, swirling into the hole, carry the imprint of time stretched nearly to breaking. Humanity has even captured the silhouette of a black hole, the dark shadow against the glowing disk of falling matter, the very outline of an event horizon where time slows to eternity. What black holes teach is that time is not a background constant. It is fragile, responsive, and at its limits, almost unrecognizable. Near Earth, relativity makes corrections of microseconds. Near black holes, it becomes a wall between realities. Here, the bending of space-time does not merely slow clocks. It separates worlds, one in which the faller moves on, another in which he is forever frozen. The paradox is not resolved. Relativity tells us how events appear, but not how to unify the two perspectives. It hints that at the horizon, the very fabric of reality is stretched to a point where classical physics no longer suffices. To understand fully what happens inside requires a deeper framework, one that unites relativity with quantum theory. Until then, the black hole remains a frontier not only of space, but of time itself. The descent toward a black hole reveals the most haunting lesson of relativity. Time is not a single thread binding all observers together, but a fabric that can be stretched, twisted, and ultimately torn apart by gravity. Near the event horizon, this truth emerges with merciless clarity. For the outside observer, a falling star, a probe, or even a human traveler never crosses the horizon at all. Its image lingers, redder and dimmer with each passing moment, until it fades into invisibility. For the falling traveler, however, the journey continues, time flowing steadily until the horizon is crossed without resistance. Two stories, both true, forever divided. Once inside, the strangeness deepens. The coordinates of space-time themselves invert. Outside the horizon, time drives every being forward, while space allows freedom of movement. Inside, the radial direction inward becomes as unstoppable as the ticking of a clock. You cannot remain at the horizon. You cannot turn back outward. You cannot delay the inevitable. The singularity at the center is no longer a place in space you may choose to approach. It is a moment in time you must encounter, as unyielding as tomorrow's sunrise. This is the most chilling aspect of black holes. They do not simply trap matter, they consume futures. To fall within is to inherit a destiny written into geometry itself. No force, no engine, no decision can change it. The singularity lies ahead in your personal timeline, as unavoidable as aging, as certain as death. It is not a choice of path, but the very structure of the path itself. And yet, what is the singularity? Relativity describes it as a point of infinite density, a place where the equations that describe space-time collapse into meaninglessness. But infinities are warnings, not destinations. They signal the breaking of a theory, the limit of its reach. At the singularity, general relativity itself falters. The known laws of physics dissolve. Time, space, matter, energy, all are pressed into forms beyond the grasp of current understanding. It is the edge of knowledge, the boundary where a new theory must take over. The paradoxes that arise here echo into the foundations of science. What happens to the information carried by the matter that falls in? Does it vanish forever, violating the principles of quantum mechanics? Or is it somehow preserved, woven into the horizon, or radiated back in subtle ways? The black hole information problem remains one of the greatest unsolved riddles of physics, a puzzle born from the collision of relativity and quantum theory. It is here, at the boundary of a black hole, that the true nature of time may yet be revealed. Even without entering the abyss, the influence of black holes stretches across the universe. They sculpt galaxies, drive jets of radiation that blaze for millions of light years, and power the brightest quasars in the cosmos. And within each, time is warped almost beyond recognition. Black holes remind us that time is not universal, not absolute. It is fragile, personal, and at the extremes, nearly torn apart. The gentle warps of everyday life on Earth are mere whispers of this reality. the corrections made for satellites and airplanes pale compared to the slowing of seconds at the horizon. Here, relativity reaches its climax. Time is not only slowed, it is fractured, inverted, and consumed. To approach a black hole is to approach the ultimate master of time. And yet, the universe is more than its abysses. Beyond the horizons of black holes lies the grander stage of the cosmos itself. Galaxies drift apart, space stretches, and the expansion of the universe reshapes the very ticking of cosmic time. If gravity can bend seconds near stars, then what does the growth of the universe do to the flow of epochs? The next step in our journey is to lift our gaze from the abyss and ask how time unfolds on the largest scales of all, across the fabric of the cosmos itself. Time is not only shaped by motion and the pull of gravity near stars or black holes. It is also stretched and sculpted on the grandest stage of all, the universe itself. If black holes show how time can nearly freeze at the edge of collapse, the cosmos shows how time can expand with the growth of space. To speak of time on a universal scale is to step into a rhythm unlike any other, a clock that measures not seconds or centuries, but the unfolding of galaxies and the birth of worlds. At the dawn of the 20th century, astronomers believed the universe was eternal and unchanging. The stars seemed fixed in the heavens. The galaxies were not yet recognized as distant islands, but thought to be clouds within our own. Then came the revelation that the cosmos was expanding. Light from galaxies carried the telltale signature of redshift, stretched to longer wavelengths as space itself grew. Edwin Hubble and his colleagues showed that the farther a galaxy is, the faster it recedes. The universe was not static. It was dynamic, alive, swelling outward like the surface of a balloon. This expansion reshaped the very idea of cosmic time. If galaxies are rushing apart, then at earlier epochs, they must have been closer. Extrapolate backward, and the universe contracts into a denser, hotter state. The idea of a beginning, a moment when space and time themselves emerged, took root. What had once seemed eternal became finite. The universe carried not only space, but also an age. Time itself had a birthday. In this vision, time is not an independent flow detached from the cosmos. It is inseparable from the expansion of space. Every photon traveling across the universe stretches with the growth of space, its wavelength elongated, its frequency slowed. This stretching of light is a stretching of time itself. A clock in a distant galaxy does not tick in step with a clock on Earth, for the expansion of space between them dilates the rhythm of signals. The universe imposes its own tempo upon all who live within it. Astronomers have learned to read this cosmic time by studying the light of ancient stars and galaxies. The faint glow of the cosmic microwave background, the afterglow of the Big Bang, is a snapshot of the universe when it was only a few 100,000 years old. Its photons have traveled for more than 13 billion years, stretched by the swelling of space into microwaves that fill the sky. To observe this glow is to look back not only in distance, but in time. To witness the early universe preserved in the very fabric of light. Cosmic time is different from the personal time of individuals, clocks, or planets. It is the shared history written across the entire universe, the measure of how long it has been since the beginning. Astronomers define it not by a universal present, which relativity forbids, but by the age of the cosmos as measured in its expansion. Each galaxy participates in this rhythm, carried apart by the stretching of space, each living within a timeline that began in the same fiery dawn. To live in such a universe is to recognize that time itself is tied to the fate of the cosmos. The tick of every second is bound to the swelling of space, the cooling of radiation, the formation of stars, and the slow dance of galaxies. Time is not a backdrop, It is a participant in the unfolding of creation. The universe carries its own clock, and humanity is only now learning to read its face. But this cosmic time is not steady. Just as gravity can bend seconds near a star, the density of matter and the presence of dark energy shape the tempo of expansion. The universe has accelerated and decelerated across its history, speeding and slowing its growth. To measure cosmic time is to measure not only the flow of moments, but also the shifting balance of forces that drive the evolution of everything. If Einstein's vision revealed that time bends near mass, Hubble's discovery revealed that time itself stretches with the expansion of the cosmos. The two are not separate stories, but chapters of the same tale. The universe is not only filled with timescales of stars and planets, it is itself a clock, beating to the rhythm of creation and expansion, carrying every galaxy and every life along with it. The expansion of the universe revealed a truth as profound as Einstein's bending of space-time near mass. It showed that time itself is not a detached thread, but a rhythm woven into the growth of the cosmos. Every galaxy receding, every photon stretched, every ancient echo heard in the night sky is a mark of time's fabric expanding. To study the heavens is not only to look outward in distance, but also backward in time. The light from a distant galaxy does not tell us what it is now, but what it was billions of years ago, when the universe itself was younger. This is the essence of cosmological redshift. As space expands, the waves of light traveling through it are drawn out. Their crests grow farther apart, their colors shift toward the red, their frequency slows. Because frequency is tied to time, this stretching is not merely a visual effect, it is a stretching of time itself. A cosmic heartbeat that once pulsed many times per second in the early universe arrives today as a slower rhythm, dragged by the expansion of space. The very signals we use to measure the cosmos are transformed by the growth of the fabric through which they travel. Consider the cosmic microwave background, the faint radiation that fills the sky. When it was first released, the universe was a glowing plasma, dense and hot, its light blue, white and blinding. Those photons have traveled for over 13 billion years, stretched until their wavelengths are 1,000 times longer, cooled into microwaves invisible to the eye. The light is slower now, its frequency diluted by the expansion of the cosmos. The glow is not just a picture of the early universe, it is a measure of how time itself has been stretched across eons. This cosmic stretching means that the universe has no single, universal present. Events that seem simultaneous from one vantage are not simultaneous from another. A star exploding in a distant galaxy today may already be long gone by the time its light reaches us. The deeper we look into space, the further back we look into time until we are peering close to the very birth of the cosmos. The universe is layered with epochs, each revealed in the light that has journeyed across billions of years. Astronomers define cosmic time not by simultaneity, but by the age of the universe as measured in its expansion. In this framework, all galaxies share a beginning, a moment when space and time first ignited in the Big Bang. Each moment since is marked by the scale of the cosmos itself, by how far galaxies have drifted apart, by how stretched the ancient light has become. To ask what time it is on the scale of the universe is to ask how old the cosmos is, how long it has been since the first moment when expansion began. And this age is not a constant rhythm. Just as gravity bends the ticking of clocks near a star, the forces shaping the universe bend the tempo of expansion. In the early epochs, when matter and radiation were dense, gravity slowed the expansion, tugging galaxies inward. Later, a mysterious energy began to dominate, pushing space apart at an accelerating pace. Dark energy, unseen yet overwhelming, now drives the growth of the universe. quickening its expansion and stretching time more and more. The cosmic clock is not steady. It beats to a shifting rhythm, sometimes slower, sometimes faster, depending on the balance of forces written into space-time itself. For human beings who measure their lives in decades and their civilizations in centuries, such scales are almost incomprehensible. Yet every person is carried along by this rhythm. Every breath, every thought, every heartbeat unfolds within a universe whose very fabric is stretching. The expansion may be imperceptible in daily life, but it is as real as the ground beneath our feet. It is the stage upon which galaxies drift and stars are born. It is the tempo that marks the age of everything. To live in this universe is to realize that time is not absolute. It is tied to gravity in local fields, and it is tied to expansion in the cosmos as a whole. Time is bent near a planet, slowed near a star, nearly stopped at a black hole, and stretched across the growth of the universe itself. Every clock, from the simplest wristwatch to the ticking of galaxies, is bound to the same truth. Time is not steady, but sculpted. The unfolding of cosmic time can be imagined as a great symphony, each movement marked by the shifting forces that shape the universe. In the earliest moments after the Big Bang, when the cosmos was less than a heartbeat old, time flowed through an ocean of energy so dense that matter and light were inseparable. The expansion was furious, rapid beyond comprehension, a storm of creation that stretched space itself at speeds faster than light could travel within it. This was inflation, a fleeting instant that set the stage for everything that would follow. As the universe cooled, particles formed, then atoms, then the first light was free to stream outward. This light became the cosmic microwave background, still visible today, stretched thin and cold, but carrying the memory of that ancient time. Billions of years later, astronomers would look into the sky and see not just points of light, but messages from the young universe, preserved in the photons that had traveled across the eons. Each photon is a clock, its frequency slowed by expansion, a marker of how cosmic time has unfolded. Galaxies formed, stars were born, heavy elements were forged in furnaces of nuclear fire. Cosmic time was measured not in seconds but in epochs. The first billion years when galaxies assembled, the next several billion when stars like the sun ignited, the later billions when planets formed and life emerged. Each era carried its own rhythm, its own measure of time tied to the scale of the universe. To speak of cosmic time is to speak of these epochs, each one layered atop the other like chapters in the story of existence. And still, the tempo shifted. In the early universe, gravity dominated, slowing the expansion as matter tugged against the outward rush. But as billions of years passed, the balance changed. A mysterious force known as dark energy emerged, faint yet inexorable, driving galaxies apart at an accelerating pace. The cosmic clock quickened again, space stretching faster than gravity could resist. Today, the universe expands at a rate that grows ever swifter, and the future is one of increasing separation, galaxies receding until their light no longer reaches us. Cosmic time stretches forward into an era where the universe becomes cold, dark, and isolated. For human beings who live in such a narrow slice of this grand timeline, the immensity of cosmic time is both humbling and inspiring. A single lifetime is a whisper against billions of years. A civilization rises and falls in the blink of a cosmic eye. Yet within that blink, humanity has learned to measure the age of the universe, to read the history written in its light, to trace the rhythm of its expansion. Against the vastness, the act of knowing becomes an achievement of its own. The cosmic clock teaches that time is not uniform. It bends near masses, it halts near horizons, and it stretches with the universe itself. there is no single beat to which all reality marches. Instead, there is a symphony, layered and complex, where local times and cosmic time weave together. A clock on Earth ticks one rhythm, a clock near a black hole another, and the clock of the universe beats yet another, measuring not seconds, but epochs. In learning this, humanity has come closer than ever to understanding the nature of time. Yet even now the picture is incomplete. Relativity tells us how space-time curves, how clocks tick under gravity, how the cosmos stretches its epochs. But relativity is not the final word. At the singularities of black holes, and at the beginning of the universe itself, relativity breaks down. The equations collapse into infinities, and time seems to lose meaning. To go further, we must turn to the next frontier, where gravity meets quantum theory. What is time in a universe made of quantum fields and probabilities? Is it fundamental, or does it emerge only from deeper structures of reality? The problem of time remains one of the most haunting puzzles of modern physics. And to face it, we must venture beyond relativity into the uncertain landscape of quantum gravity, where time may not flow at all. The triumph of Einstein's relativity was to reveal time as a flexible dimension, one that bends with motion, slows with gravity, and stretches with the expansion of the cosmos. Yet relativity is not the whole story. For all its beauty, it falters at the most extreme edges of reality, at the singularities of black holes and at the birth of the universe itself. There, the fabric of space-time is driven to conditions so extreme that relativity collapses. What takes its place is uncertain, but physicists know it must be a theory that unites relativity with the other great pillar of modern science, quantum mechanics. Quantum mechanics paints a universe very different from relativity. It describes a world not of smooth curves and continuous flows, but of probabilities, fluctuations, and discrete quanta. Time in quantum theory is simple, even primitive. It is treated as an external backdrop against which particles evolve. Equations describe how a quantum state changes with time, but time itself is not part of the dance. It is a stage, not an actor. Relativity, by contrast, insists that time is dynamic, inseparable from space, bent by energy and mass. The two visions are not merely different, they are contradictory. Relativity says time is flexible. Quantum mechanics says time is fixed. This clash is nowhere more apparent than in the Wheeler-DeWitt equation, one of the attempts to merge relativity with quantum theory. When physicists wrote the equation that should describe the quantum state of the universe as a whole, something startling emerged. Time disappeared. The equation contained no ticking, no flowing, no arrow pointing from past to future. It described a universe that simply is, timeless and static. The flow of time, so fundamental to experience, seemed to vanish in the mathematics. Some physicists interpret this to mean that time is not fundamental at all but emergent. It may arise only when parts of the universe interact, when entanglement creates the illusion of sequence, when change gives the appearance of flow. In this view, time is not a river, but a pattern, not a dimension, but an effect. To ask about the passage of time at the deepest level may be as meaningless as asking about the sound of a single violin string without the orchestra. Other approaches to quantum gravity suggest different visions. In loop quantum gravity, space-time itself is quantized, made of tiny loops woven together like a fabric. Time in this picture is not continuous, but granular, built from discrete moments that link together. In string theory and its cousin, the ADS-CFT correspondence, space-time may emerge from networks of quantum entanglement. Time, in this vision, is a hologram, an emergent property of deeper structures that do not themselves experience time at all. What all these approaches share is a challenge to common intuition. Time, which feels so immediate, so undeniable, may not exist as we think it does. At the deepest level of the universe, there may be no ticking at all, no before or after, only relations, patterns, and probabilities. What we call time could be a construct born of the way observers perceive change, not a fundamental feature of reality. And yet, this cannot be dismissed as abstract philosophy. The problem of time is not a thought experiment. It is a real obstacle to building a unified theory of physics. Until scientists understand what time truly is, they cannot fully describe the birth of the universe, the fate of black holes, or the structure of space-time at the smallest scales. Time, once thought the most obvious of all dimensions, has become the most mysterious. The clash between relativity and quantum mechanics is more than a technical disagreement. It is a fracture at the heart of science, a crack in the foundation of knowledge. Relativity says time is a flexible fabric. Quantum theory says time is a fixed backdrop. Attempts to reconcile them erase time altogether. Somewhere in this puzzle lies the truth, waiting to be discovered. The Wheeler-DeWitt equation was one of the first great hints that time may not be what it seems. Derived in the 1960s, it was meant to combine the smooth geometry of general relativity with the probabilistic machinery of quantum mechanics. But when the dust settled, something shocking was left on the page. The equation contained no time. It described the quantum state of the universe as a whole in a static, timeless way. There was no arrow, no flowing sequence from past to future, only a vast configuration space of possible states existing together. This strange result has been called the problem of time. How could the most familiar aspect of reality, the ceaseless passage of moments, vanish from the deepest equations? To some, it suggests that time itself is not fundamental, but emergent, an illusion woven from correlations. If one part of the universe changes relative to another, observers within it may experience this as the flow of time. But in the deepest description, there is no underlying tick, only relations. The heartbeat of reality may not be a rhythm at all, but a pattern that human minds interpret as rhythm. One of the most intriguing ideas in this direction comes from the role of entanglement. In the quantum world, particles can be linked across distance, their properties correlated in ways that defy ordinary causality. Some physicists propose that time itself may arise from such entanglement. The passage of time could be nothing more than the unfolding of correlations, the growth of complexity in quantum states. In this picture, time is not a fundamental backdrop, but an emergent effect of information. Loop quantum gravity offers another radical vision. It suggests that space-time is built from discrete chunks, woven together like a fabric of loops. If space is granular, then time too may be granular, advancing not smoothly, but in tiny jumps. A second, in this view, is not an indivisible unit, but the sum of countless quantum ticks. Between those ticks, there is no time at all. The continuity we feel is an illusion born of scale, much like a movie seems fluid, even though it is made of still frames. String theory provides yet another perspective. In certain formulations, space-time itself may be emergent from a deeper reality of vibrating strings and multi-dimensional structures. The ADS-CFT correspondence suggests that space-time and time within it could arise as a holographic projection from quantum entanglements on a lower dimensional surface. If this is true, then time is not fundamental, but a shadow, a phenomenon that appears only when viewed from the right angle, like depth in a hologram. Each of these attempts highlights the same unsettling theme. Time, which feels so immediate and inescapable, may not exist at the bedrock of reality. It may be a construct, a perception, an emergent property of deeper laws that have no use for past or future. The flow we feel may be like the flow of wind across the skin, real in experience, but not a fundamental property of the air molecules themselves. This challenges more than physics. It challenges philosophy, consciousness, and identity. If time is not fundamental, what does it mean to say that a life has a beginning and an end? What does it mean to speak of cause and effect, of memory and anticipation? These are built upon the assumption that time flows. If the flow is emergent, then so too may be the stories we tell ourselves about existence. Physicists are divided. Some believe that time is too deeply tied to causality and entropy to be dismissed. Others believe that clinging to time as fundamental may be the very thing preventing progress in unifying quantum mechanics and relativity. The debate continues, fueled by mathematics, experiments, and the stubborn insistence of the human mind that time must be real. But perhaps the truth is more subtle. Perhaps time as we know it is not the ultimate description, but a useful approximation, valid for the scales in which human beings live and galaxies evolve, yet destined to dissolve at the extremes. Just as Newton's clockwork gave way to Einstein's curved space-time, Einstein's vision may one day give way to a deeper theory, where time as we know it is no longer necessary. If time is not fundamental, then why do we experience it so vividly? Why does every moment feel like it pushes against us, slipping away into memory while the future remains hidden? If the Wheeler-DeWitt equation shows a timeless universe, and if quantum theories suggest that time may emerge only from correlations, why should consciousness unfold in a sequence at all? This is where physics and philosophy meet, where science is forced to confront not only the equations of the cosmos, but also the experience of living within it. One answer lies in entropy, the measure of disorder. The second law of thermodynamics tells us that entropy tends to increase. An egg can shatter into pieces, but the pieces will not reassemble into a whole. A glass of hot water cools in a room, but the room does not spontaneously warm the glass. These asymmetries give time its arrow. They create a distinction between past and future, between memory and anticipation. In a timeless universe of possible states, the increase of entropy is what defines the direction we perceive as the flow of time. The arrow is not fundamental, it is statistical, but it is real enough to give rise to history, to causality, to the story of our lives. Another answer may lie in information. The universe is not only matter and energy, it is also information, patterns of correlation between systems. Quantum entanglement ties particles together, and as these correlations evolve, observers perceive change. Some physicists argue that time is nothing more than the growth of information, the weaving of correlations across the quantum fabric. From this perspective, the flow of time emerges whenever there are observers to notice differences, whenever patterns grow more complex. Time may be what it feels like to live inside the unfolding of information. Speculative frameworks go further still. In loop quantum gravity, the smallest scales of space and time are granular, like pixels in a cosmic image. Time in this view is a sequence of discrete moments, a series of quanta of change. In string theory and the ADS-CFT correspondence, space-time and time itself emerge from deeper mathematical structures of entanglement, as if reality were a hologram projected from a hidden realm. In all these pictures, time is not erased, but it is dethroned. It is no longer a primary ingredient of the universe. It is a byproduct, a shadow, a phenomenon that arises only when deeper structures are seen in motion. The unsettling conclusion is that the most familiar aspect of existence may be the most illusory. Time, the constant companion of every breath, may not be part of the fundamental architecture of the cosmos. It may be a construct, A perception, a feature of minds that evolved to track change in a world of entropy and information. At the deepest level, reality may be timeless, and what we call the flow of moments may be nothing more than the way complexity feels from the inside. And yet, dismissing time as illusion feels impossible. Every heartbeat, every sunrise, every memory insists that time is real. Perhaps the answer lies in a middle path. Time may not be fundamental, but it is emergent and indispensable, as real to us as pressure or temperature. Just as heat emerges from the chaotic motion of molecules, time may emerge from deeper patterns of the universe. It may not exist in the equations at the foundation, but it arises in the world that those equations create. This is the puzzle that haunts modern physics. Relativity tells us that time bends and warps, that it is a dimension of space-time. Quantum theory tells us that time is an external parameter, or perhaps not present at all. Efforts to reconcile them suggest that time may be emergent, an illusion built from correlations and entropy. At the intersection of these ideas lies one of the deepest mysteries of all. What is time? For now, the question remains unanswered, but in pursuing it, humanity has come closer to seeing reality as it is, not as it appears. And in doing so, we are forced to confront the strangeness of our own experience, to ask why our minds perceive a flow when the universe may not contain one. It is here, on the boundary between physics and consciousness, that the problem of time becomes not only a scientific puzzle, but a human one. The next step in this journey is to turn inward, to examine the contrast between the physical time of relativity and quantum theory, and the psychological time of human perception. If the universe is timeless or warped, why do we feel time as steady and absolute? Why does the mind weave memory, anticipation, and awareness into a continuous thread? In seeking these answers, science and philosophy converge, and the warping of time becomes not only a property of the cosmos, but a challenge to our very sense of reality. For all that science has revealed about the warping of time, human beings continue to live as though it flows evenly, steadily, and universally. We wake, we age, we remember, we anticipate, and we feel the arrow of time moving in one direction only. This sensation is so overwhelming that it defines our sense of existence itself. Yet physics insists that this is an illusion. The flow of time, the constancy of its beat, is not written into the fabric of the cosmos, but into the structure of our minds. Why does the brain insist upon this steady rhythm? One answer lies in survival. To navigate the world, an organism must perceive change. A predator lunging, a fruit ripening, a storm approaching, all require the ability to compare now to before, to imagine what comes next. Evolution carved nervous systems to track change, to knit perceptions into a story that feels continuous. The sensation of time flowing may be nothing more than the stitching together of memory and anticipation. The mind makes a thread where physics provides only beads. Neuroscience has revealed how perception creates this illusion. The brain does not record every moment like a film. Instead, it takes snapshots, integrates them, and smooths them into a sense of continuity. The gaps vanish in the stitching, leaving only the impression of a flowing river. Experiments show that perception lags reality by fractions of a second, yet we never notice. We feel time as immediate and seamless, even though it is constructed behind the curtain of awareness. Physics and psychology thus speak in different languages. Physics says time bends, stretches, halts, even vanishes from its equations. Psychology says time flows, relentless and unstoppable. Both are true in their own domains. The human brain evolved not to reveal the universe's ultimate structure, but to keep us alive within it. A steady clock in the mind is more useful than a fractured relativity of moments. Yet this mismatch creates tension. We feel time as universal, but we know it is local. We feel the present as absolute, but relativity insists there is no universal now. We feel the future as open, but physics describes equations that are symmetric, unfolding equally forward or backward. Our intuition rebels against the strangeness of the cosmos, insisting on a flow that physics cannot find. This is why the problem of time is not only a scientific puzzle, but also a human one. It challenges not just the equations of relativity or quantum theory, but the foundations of consciousness. If time does not flow, why do we feel that it does? If there is no universal present, why do we live as though one exists? The answers may lie not in physics alone, but in the intersection of physics, biology, and philosophy. Perhaps the flow of time is an emergent property of memory. The past is what we remember, the future what we anticipate, and the present what we experience. The flow is nothing more than the mind weaving these three into a thread. Without memory, there would be no past. Without anticipation, no future. Without awareness, no present. Physics may describe a timeless universe, but the mind lives by stitching snapshots into a story. And yet, there is power in this illusion. For without it, human beings could not plan, could not dream, could not build civilizations across generations. The psychological time we carry may be an illusion compared to the cosmic truths of relativity, but it is an illusion upon which the human story depends. We live inside the rhythm our brains create, and from it we shape meaning. The strangeness of time becomes most vivid when we confront how differently it behaves in the equations of physics, compared to how we feel it in the stream of awareness. In relativity, there is no universal present. What one observer calls now may be another observer's past or future, depending on their motion and position. Yet our minds cling to the idea that the present is absolute, that all beings share the same moment. This is a useful fiction, one that allows human societies to coordinate and communicate, but it is not reality. Physics denies the existence of a single shared now. Experiments with simultaneity make this clear. Imagine two lightning bolts striking opposite ends of a moving train. To someone standing on the ground at the midpoint, the flashes may appear simultaneous. But to someone riding inside the train at the midpoint, moving toward one strike and away from the other, the flashes arrive at different times. Which is truly simultaneous? Relativity answers, neither. Simultaneity is relative, and so the very concept of a universal present dissolves. Yet no matter how many times we read this truth, we continue to feel that there is a shared now. The human mind cannot escape the sensation, even when it knows it is false. The perception of flow is equally deceptive. To physics, the laws of motion are symmetrical. They work equally well forward or backward in time. A film of two billiard balls colliding looks just as plausible in reverse as it does forward. But in experience, time is not reversible. We remember the past, but not the future. We age in one direction only, and we see cause preceding effect. This asymmetry comes not from the laws themselves, but from entropy, the tendency of systems to move toward greater disorder. The broken egg does not reassemble because such states are overwhelmingly improbable. Entropy gives time its arrow, and the brain translates that arrow into the sensation of flow. Perception of time also varies with context, a sign of its psychological roots. Moments of danger seem to stretch, each second unfolding in slow motion. Moments of joy seem to fly, hours passing unnoticed. Routine dulls the sense of passage, novelty sharpens it. These variations show that the mind is not a passive receiver of time, but an active constructor of it. Our sense of flow expands and contracts, speeds and slows, depending on emotion, attention, and memory. Physical time does not change, but psychological time is elastic. This elasticity reveals that our sense of time is not a faithful mirror of reality, but a tool shaped by evolution. It helps us learn, anticipate, and survive, but it does not reveal the cosmos as it is. In truth, the cosmos contains no universal flow, no single present, no guarantee that the future is different from the past. Relativity fractures simultaneity, entropy creates the arrow, and quantum theory may erase time altogether. Yet the mind insists on a seamless thread, a continuous now sliding into tomorrow. This tension is both unsettling and liberating. It unsettles because it shows how deeply our intuition diverges from the universe's structure. It liberates because it reveals that perception need not bind reality. What feels absolute is not. What feels eternal may vanish in deeper theories, and what feels like flow may be nothing more than the brain stitching snapshots into a story. But this story matters. Psychological time, though an illusion in physics, is the framework of human existence. It is how we tell our histories, plan our futures, and make meaning in the present. To recognize its illusory nature is not to diminish it, but to place it in context, to see it as one layer of time among many. There is physical time, warped by gravity and expansion. There is quantum time, perhaps emergent from correlations. And there is human time, the thread of memory and anticipation. Each is real in its own domain. The challenge, then, is to reconcile these layers, to live with the knowledge that our experience of time is not the whole truth. We may never feel relativity in our bones, never sense entropy in motion, never perceive the quantum timelessness beneath reality, but we can know that our thread of time is only one among many, a human melody woven into a cosmic symphony far grander and stranger than the mind can perceive. The collision between physical time and psychological time is perhaps the most profound gap between human intuition and the cosmos. Physics strips away the illusion of flow, revealing time as a dimension, as malleable as space, bent by gravity, stretched by expansion, and perhaps absent altogether at the deepest levels. Yet the mind cannot escape its insistence that time flows. We are prisoners of this sensation, living within a thread that is stitched by memory and anticipation. Relativity sharpens the fracture. If there is no universal present, then the now you inhabit may not align with the now of someone moving differently across space-time. Two events that feel simultaneous to you may not be simultaneous to another observer. To live in relativity's universe is to accept that there is no single shared moment, only a patchwork of personal timelines. Yet our perception rebels. We cling to the idea that there must be one global now, that all beings share the same present. The illusion persists, even when we know it to be false. The bending of time near gravity challenges intuition even more. A clock on a mountain ticks faster than one by the sea. A satellite in orbit experiences time differently than a clock on Earth. Yet no one living at sea level feels slower. No one on a mountaintop feels faster. Perception insists on sameness, even as physics proves otherwise. We live in distorted time without ever sensing it, blind to the warps that shape our existence. Quantum theory stretches the challenge further still. If time may be emergent, if it may not exist at the deepest level, then the very flow we feel is not just distorted, but perhaps absent. Our lives unfold in a story of past, present, and future. Yet the ultimate laws of the universe may describe only relations, not sequences. To the equations, there may be no unfolding at all. To the mind, there is nothing but unfolding. The tension is irresolvable, yet it is also fertile. It forces us to recognize that perception is not reality, that intuition is not truth. It humbles us before the universe, reminding us that our senses evolved to keep us alive, not to reveal the ultimate structure of space-time. The steady beat of psychological time is no more accurate a picture of reality than the impression that Earth is flat beneath our feet. It is a working model, useful but limited. And yet, even as physics dismantles the illusion of flow, it cannot erase its power. The stories of our lives depend on it. Without the thread of time, there is no memory, no meaning, no narrative. Physics may describe a timeless universe, but human beings live in stories, and stories require time. The illusion may not be fundamental, but it is indispensable. This duality, timeless cosmos, flowing mind, is the paradox in which we live. To study time is to discover not only the warping of seconds under gravity, the stretching of epochs with cosmic expansion, the possible disappearance of time in quantum theory, but also the stubborn insistence of the human brain to experience a continuous now. Science and perception diverge, yet both are real in their domains. Perhaps the ultimate perspective is to hold both truths at once. Time as physics reveals it is warped, fractured, emergent, perhaps even absent. Time as consciousness reveals it is flowing, steady, and absolute. We live at the intersection, building meaning from one while uncovering truth with the other. The challenge of the next step is to weave these perspectives together, to face the warped universe without surrendering the stories that make us human. And so the journey arrives at its final question. If time bends, warps, stretches, and perhaps even vanishes, what is the ultimate nature of its flow? How can we reconcile the warped seconds of relativity, the timeless equations of quantum gravity, and the flowing narrative of the mind? The final chapter will bring these threads together toward a vision of time not as a river flowing evenly, but as a fabric woven by gravity, motion, and perception, a fabric in which every life is a stitch and every star a rhythm. From the moment Newton declared that time flowed identically for all, to the moment Einstein shattered that certainty, humanity's understanding of time has undergone a transformation as profound as any in science. What was once seen as a universal river has revealed itself as a fractured fabric, bending under motion, slowing under gravity, and stretching with the expansion of the cosmos. Time is not steady. It is not absolute. It is a rhythm set by the structure of space-time itself. To look back on this journey is to see a cascade of revelations. First came the discovery that motion alters time, that a moving clock ticks more slowly than one at rest. This was the lesson of special relativity, the twin paradox made real by experiments with airplanes and satellites. Then came the deeper realization that gravity itself reshapes time, slowing its pace near massive objects, bending it at the surface of stars, halting it at the event horizons of black holes. And beyond, on the grandest scale, time is stretched by the growth of the universe, its epochs defined by the expansion of space. Each step pulled us further from the illusion of a single universal rhythm and deeper into a universe where every clock carries its own beat. And yet, even as physics has dismantled the old certainty, it has also revealed a strange harmony. Though every clock ticks differently, the rules by which they diverge are precise and universal. Time is not chaos. It is a geometry, a structure governed by equations that hold across galaxies and black holes alike. The bending of seconds may be unsettling, but it is also beautiful, a pattern woven into the very fabric of existence. For human beings, this revelation is both humbling and empowering. Humbling because it shows that intuition is blind to the deeper truths of the cosmos. No one feels the seconds slow at sea level or quicken on a mountaintop. No one senses the freezing of time near a horizon or the stretching of epochs across cosmic distances. Perception insists on steadiness, but reality bends. Empowering, because with equations and instruments, We can see beyond the limits of perception. We can measure the slowing of clocks in towers, the warping of time in satellites, the dilation of signals from galaxies. We can know what we cannot feel. The flow of time in a warped universe is not a simple river but a landscape. Valleys of gravity slow its pace, peaks allow it to quicken, horizons stretch it to eternity, and cosmic expansion draws it ever outward. To live in such a universe is to live not in one time, but in countless times, each local, each relative, each woven into the greater fabric. The seconds of your life are not the same as the seconds of a satellite above you, nor the same as the seconds near a star, nor the same as the seconds stretched across the cosmos. Yet all are part of one tapestry, bound by the laws of relativity. This vision does not erase the flow of time as we feel it. It deepens it. To know that every heartbeat is slowed by Earth's gravity, that every step you take shifts your clock by imperceptible fractions, that the stars above you are ticking in rhythms not quite your own. This is to live with awe. The illusion of absolute time may be gone, but in its place is a richer truth. Time is alive, responsive, sculpted by the mass and motion of the universe itself. The question remains, what is time at its deepest level? Is it fundamental, as relativity suggests, woven into space-time itself? Or is it emergent, as quantum theory hints, a construct rising from correlations and entropy? The answer is not yet known, but perhaps the uncertainty is itself a gift. For in not knowing, we are invited to keep asking, to keep probing, to keep pushing the limits of understanding. Time remains both the most familiar and the most mysterious of dimensions, a frontier at the edge of knowledge. What is certain is that the old vision has been left behind. Time is not the steady metronome Newton imagined. It is a flexible, fractured, and wondrous phenomenon. It bends to gravity. It stretches with expansion. It may even dissolve into emergence at the quantum level. And yet, it is also the thread of human life, the story woven by memory and anticipation, the rhythm that gives meaning to existence. To live in a warped universe is to live in two times at once. The physical time of relativity, bent and stretched across space-time, and the psychological time of perception, flowing steadily in the mind. The two may never be reconciled fully, but together they form the reality in which we exist. A universe where seconds are not absolute, where the flow is not steady, where time itself is written by gravity. The picture of time that emerges from relativity is nothing short of cinematic. Imagine standing on a mountain peak with the sun setting in crimson light. The watch on your wrist ticks ever so slightly faster than the clocks of the city far below. You cannot feel it, yet it is real. The mountain frees you from a fraction of Earth's gravity, and in that freedom time itself loosens its grip. A climber lives seconds just a little quicker than those in the valley, their lives diverging in ways too small to sense but precise enough for physics to measure. Now imagine a satellite orbiting high above Earth. Its clock ticks differently still. Its speed slows it down. Its altitude speeds it up, the two effects competing in a delicate balance. Engineers adjust for both, their calculations aligning the flow of time across Earth and sky. Without those corrections, navigation would falter, maps would fail, planes would stray. Every direction we follow, every signal we send, depends upon the hidden truth that time is warped. Take a step further. Imagine a spaceship approaching a neutron star, a collapsed remnant of unimaginable density. Its gravity pulls so strongly that mountains would flatten in centimeters. A clock near its surface runs so slowly compared to a clock far away that the difference is no longer negligible, but profound. A single hour near the star might equal years in the wider universe. What is an afternoon to one observer could be a lifetime to another. Here, relativity ceases to be subtle. It becomes overwhelming. And then the ultimate vision, the event horizon of a black hole. To approach it is to enter a place where time stretches toward infinity. A falling traveler experiences moments normally, crosses the horizon without resistance, and moves inevitably toward the singularity. But to those watching from afar, she slows, her signals redshift, her image freezes. For the distant observer, she never arrives. Her final seconds linger forever at the edge. The horizon is not merely a boundary of space, it is a fracture in time itself. Beyond even this lies the cosmic stage, where galaxies drift apart and light stretches across billions of years. The universe expands, and in that expansion time is stretched as well. Photons from the early universe arrive to us elongated, their frequency slowed by cosmic growth. To look into the night sky is to see billions of years at once, each star a marker of a different epoch, each galaxy a clock telling its own time. The universe is not simply old, it is layered with histories, all stitched together by the stretching of space. Relativity has revealed that every place, every speed, every mass carries its own tempo. There is no single universal rhythm. Instead, there is a chorus of clocks, each ticking in harmony with the geometry of space-time, each obeying the same elegant rules yet singing its own measure. From mountaintops to satellites, from neutron stars to black holes, from Earth to the edge of the cosmos, relativity rules every clock. This vision reshapes our place in the universe. We are not detached observers standing outside time, but participants immersed in its warps and flows. Our lives unfold within the slowed seconds of Earth's gravity. Our technology depends upon corrections written into Einstein's equations. And our understanding of the cosmos is drawn from light, stretched by billions of years of expansion. Time is not the backdrop of our story. It is the story. And in this story, there is wonder. The warping of time is not only a challenge to intuition, but also an invitation to awe. To know that every second of your life is shaped by the planet beneath your feet, that the cosmos itself stretches your moments, that the deepest abyss can freeze time to eternity, is to see existence as more than mundane. Time is not the river we once thought. It is a vast and dynamic ocean, its currents bent by mass, its tides driven by expansion, its depths perhaps timeless at their core. This is the legacy of relativity. It does not erase time but transforms it, showing us that the flow we take for granted is neither absolute nor universal. It is local, relative, sculpted by the cosmos itself. And in learning this, we learn something deeper, that the universe is not only stranger than it appears, but also far more beautiful. The story of time ends where it began, with the human desire to find certainty in a world that feels fleeting. For centuries, people trusted that the seconds of a clock were the same for all, that past, present, and future marched forward with universal steadiness. It was a comforting vision, simple and absolute. But the journey of science has stripped away that illusion, revealing something far stranger and far more beautiful. We now know that time bends with motion. It slows for the astronaut racing through space. It shifts for the traveler circling the globe in an airplane. It changes for satellites guiding ships across oceans. We know that time bows to gravity. It ticks slower in valleys than on mountaintops, slower on Earth than in orbit, slower still near neutron stars and black holes. We know that time stretches with the expansion of the universe, its very fabric dilating as galaxies drift apart, its ancient light drawn into longer and slower waves. And we suspect that at the deepest level of reality, time itself may not be fundamental at all, but emergent, a construct woven from entropy, information, and entanglement. Against this backdrop, The steady flow of time that we feel in every heartbeat is both an illusion and a gift. It may not be written into the equations of physics, but it is written into the structure of consciousness. Without it, there would be no memory, no meaning, no story. Our lives unfold as narratives stitched by the mind, even as the cosmos unfolds in rhythms that defy that narrative. We live in a dual reality, the psychological time that feels absolute, and the physical time that is warped, fractured, and perhaps timeless at its core. To embrace this is to stand in awe of the universe. Time is not the river we once imagined. It is a fabric, stretched and sculpted by mass, by motion, by expansion, and perhaps by quantum patterns hidden beneath it all. Each clock, each life, each star follows its own beat. The cosmos is not united by one rhythm, but by countless rhythms, woven into a symphony without a single conductor. And yet, there is harmony. The warping of seconds by gravity, the dilation of time at speed, the stretching of epochs across space, all follow the same elegant rules. Einstein's equations bind them together, showing that beneath the strangeness lies order, beneath the fracture lies unity. Time is relative, but relativity itself is universal. It is a geometry that holds across planets and galaxies, across black holes and the universe entire. In this warped universe, gravity is not only the shaper of motion, but the writer of rhythm. It tells clocks how to tick, photons how to travel, galaxies how to drift. It sculpts the seconds of human life and the epochs of cosmic history. Gravity, once thought only a force, has revealed itself as the author of time. So the story closes with a new vision. Time is not steady, not absolute, not universal. It is fragile, local, relative, perhaps emergent. It bends, it warps, it stretches, and at its limits it may dissolve. And yet, within that strangeness lies beauty. For to live in a warped universe is to live in a cosmos that is alive, dynamic, and filled with wonder. Time is not the river we once thought it was. It is the ocean that carries us, shaped by the stars, sculpted by the galaxies, and written by the gravity that binds it all. And in the end, it is not we who keep time. It is the universe itself that keeps us, ticking in rhythms beyond our perception, carried in a flow that bends and warps but never ceases, the eternal heartbeat of a cosmos that is stranger and more magnificent than we could have ever imagined.